Hi, I'm Ben-Yaakov. This presentation is entitled Active Ripple Filters for Switch Mode Converters. Let's see first of all, where do we find the ripple? Actually, we find it at the output and the input of a switch mode converter. Here I'm showing a boost converter, the inductor, transistor, diode, and an output section. And as this switch is turned on and off, the current through this diode injected into the output section will look like this, pulses of current, and of course therefore we're going to have a ripple on the output to look like this. Now of course we can increase the capacitor, this will lower a little bit the ripple, but then because of the ESR, the equivalent series resistor, we're going to have a ripple even if the capacitor is very large. So in some applications which are sensitive to ripple, there is something else you have to do here, and of course the simple way would be to put a LC section with an inductor to reduce the ripple. But here we are talking about active circuit solutions. Another area in which you have to worry about the ripple is the input side. Here is the AC side, and I'm showing here a flyback converter, this is a rectifier, a filter capacitor, a switcher, and magnetic element and output section. Now the current in this branch here to the magnetic device we look pulsating like this, and therefore the voltage across this capacitor is going to have a ripple on it. Now if I look at the current off the line, I'm going to see the low frequency component, and being a sort of a filter type, a capacitive filter configuration, of course we're going to have some peak current, but this is not the issue I'm talking about here. I'm talking about now the ripple which is superimposed here, that you'll see current ripple. And if you look at the spectrum of this thing, you're going to see components all over the place up to very high frequencies. Okay, now this is not a problem of the end user, that is the user here doesn't worry too much about this ripple. However, there are some standards which limit the amount of ripple that you are allowed to inject into the line, and this is measured by the so-called LISN, which is the line impedance stabilization network. And then the output of this thing is going to a spectrum analyzer, and you have to make sure that the amount of ripple injected through this device under test is lower than the permissible limit. Now the LISN itself is a sort of a filter, and these two inductors actually blocking the ripple, while the ripple will find its way through these branches and generating a voltage across this resistor. It could be actually 1 kilo ohm or 50 ohm. And if it's a 50 ohm, you go into a spectrum analyzer with a 50 ohm input. And here you measure actually the voltage developed on these resistors as a function of this ripple current which is passing here. And of course, you have to make sure that this measured value are lower than is permitted by the standard. Now the simplest way to attenuate a ripple, and here I'm showing a output side, this is the output of a switch of a regulator, is the simplest way would be to put a transistor in series. And what is really happening here is that we have a low pass filter, so the voltage here has much less ripple than the voltage here. And this is sort of a emitter follower, so the voltage here will be quieter than here. So there is an attenuation due to this filter. The breakpoint is dependent on the size of the capacitor, and of course this resistor. So it's 1/2 pi RC. This is the breakpoint, and you'd like to be somewhere here with high attenuation. However, there is a problem here, and this is the power dissipation. There is a voltage across this transistor which is equal to VBE plus the drop on this resistor. Here it is. Now the drop on this resistor is a function of the current. This transistor has to pass DC current because we're talking about a regulator, we're talking about a load that requires the current. It's the whole purpose here. So the base current now is equal to the output current over HFE, large HFE, and as the current is increasing, IB will increase and the voltage drop on this resistor will be larger so that VCE will be larger. Now, you can of course reduce the resistor, the size of the resistor, but then if you do that, the breakpoint will move to a higher frequency and of course the effectiveness of this whole configuration will be lower. So there is a problem here, and this is why this really is suitable for really low power, maybe tens of milliamps, and that's it, not for high power. Another low power solution would be to have a parallel or shunt connection. Here we have a transistor again, but it is in a shunt configuration. This is the noisy side, this is the load side. Now we look at the ripple here, and actually it's fed to the base of the transistor at high frequency. The impedance is very low, so the voltage here is about the voltage here. I'm talking about the ripple voltage. And looking at it as a emitter follower, the voltage here will be also this V in, and therefore the current will be V in over R8, which is 8.25 ohms in this case, in this article. And this will be the current here, and of course in a transistor the collector current just about the same as the emitter current. So we are sinking here ripple current. So we have a ripple current here, we are sinking it here, and therefore the difference which goes to the output, to the load, will be smaller. So this is a shunt connection, and you absorb the current here rather than attenuate it as we've seen it before. Now obviously there's another issue here of power dissipation. In this case it's depending on this resistor, which you must have in order to get a attenuation here. So this configuration is again for low power. So however, this idea of shunt connection and current sinking is being used for high power too, and mainly for the input side. As a matter of fact, most of the papers on the subject are looking at the input side. So here's one of the earliest papers, a 1995 paper by Hamid and Tho, and the configuration is again, this is the noisy side, this is the quieter side, it's the load side. This is actually, in the case of the input, this will be the AC side. You like it to be quiet. So the noise coming here is absorbed here, or part of it, and I out, which is the difference, is much lower than the ripple current that you started with. Now, in order to be effective, of course, you have to generate this dependent source as a function. You have to control it as a function of the current here. And what they did actually in this paper, they have made it a function of both the ripple here and even the current ripple here, which is affecting this current sinking. And here is the circuit. Let's start with, said on the left side, we have a current sensor, and the current reflected to the output is now dropped on this resistor. Part of it is sensed and fed to this amplifier. Also, there is a DC bias here, which sets the value of the gate of this transistor to the linear region. And this configuration of this amplifier is actually configured as a non-inverting amplifier. We have the same thing on the other side, and then this current is now fed through or passing through this configuration and practically through the capacitor. There are two capacitors because of the, at high frequency, the low ESR capacitor will be more effective. And this is just for the biasing of these transistors. Now the amplifier, as I've said, I'm just copying it here in a more general form, generic form. We have the input, here it is, this is the input. We have the feedback, this is the feedback, here it is. And the output is feeding the gate, and therefore there is a sort of a gain between Vin and this voltage here, which is depending on the value of these impedances. And here this expression ZF over plus Zin over Zin, and this voltage now of course is causing a current to flow through this resistor, which is this 22 ohm resistor, and this current is now also the drain current. Okay, so it's similar to what we've seen before. ZF is large, here it is. Zin is small, here it is, at mid frequencies, and therefore you have a high gain, therefore you have a high current, and this current is now actually absorbing the ripple and shorting it out. So this is a implementation of the idea of the shunt connection for high power that had been demonstrated, as I said, some years ago. Now, a recent paper is using the same idea, although the implementation is a little bit different. We have sensing of the input voltage here, which is then fed to this amplifier, and then generating a current, which is actually passing through here, and again we have a sinking of the current. So this configuration is very similar, except that the sensing is of the voltage. This is actually the noisy part, and this is the impedances are actually some of these are the parasitic impedances. This is the impedances that are added on, and they are using actually to attenuate the ripple voltage or absorb the ripple current. Now here they're showing the noise level before adding this active filter. Here it is, and this is after adding the filter. The red line here is the norm, is the standard, so you have to be below this line, and after adding the filter, indeed they are below this line. Now let me just analyze the circuit here to understand what is going on, and I've redrawn it in a little bit different configuration. Maybe it'll be easier to understand what's going on. So we have Vin, which is the voltage here. We have CF, which is this capacitor fed to the virtual ground of this amplifier. C out, this is here, this is C out, and we have RF. Now, the current flowing here is Vin, this is ground here, so it'll be Vin times J omega C sub F. And the V out is the same current is passing through this resistor, so it'll be minus, because of the direction, minus this expression here. And the current through this capacitor now is the voltage difference across it over the impedance, and it comes out to be this current. And therefore, the impedance that you see as you look into this circuit is 1 over omega square RF, CF, and C out. Now this is it's an AC impedance, and it's not passing any current. First of all, because they are capacitors, so there's no DC current here, only AC, and you can actually see that as omega goes to 0, this impedance goes to infinity, so everything is in order. Now, just take an example, say the capacitor of 1 microfarad, the resistor is 1 megohm, and the frequency is 100 kilohertz, so the omega is 2 pi times this. And as we plug in the numbers, we are getting Zin is 0.4 milliohm, very, very low. So we have a AC sort of a resistor here of milliohm, and of course it'll attenuate the noise coming from here, leaving very little noise to the output. So this is the idea behind this circuit. However, the analysis I've made is assuming an ideal amplifier. with infinite bandwidth and infinite gain. Well, we don't have anything like this in reality. And there are many issues here that make implementation of this idea very complex. First of all, we have stability issue because this circuit tends to go into oscillation because of the limited and the phase shift of the amplifier. We need a high frequency amplifier to accommodate all the frequencies to the end of the bandwidth of interest. And of course, we need a power amplifier because in a power circuit, the ripple current is fairly high. So these are the problems, and you're welcome to look at this paper to see how the authors implemented this amplifier. Actually, they have built an amplifier for this purpose. Now, there are many other possibilities for implementation of an active filter. Now, we have seen this one, and sensing the voltage here, sinking the current here. Now, rather than measuring the voltage or sensing the voltage, you can have a current transformer generating a voltage which is proportional to the ripple here, and then sinking the current. Okay, so this is similar idea. It's a shunt connection. However, you can have a series connection, and in this case, let's look at this configuration. We have a voltage sensing the voltage here, generating a error signal, which is now fed to a sort of a voltage transformer. So we have a primary and a secondary, which is now developing a voltage which is opposing this source. Now this is the equivalent circuit of the noise, and this is the sort of the AC side. So the idea here is to build a voltage which is opposing the polarity, instantaneous polarity, I should say, of the noise here, and therefore limit the ripple current here. And of course, rather than sensing the voltage, you can sense the current, or the residual current, I should say, and then amplify it and generate this opposing voltage in series with this noise. So these are the possibilities, and people have shown implementation of these various possibilities. Now, the authors of this paper actually built a filter. These are the PCB configuration of this filter, which is shown here. This is a circuit diagram. This is the AC side. This is the noisy side. This is like the regulator or the switch mode converter. And this is here the listen. Okay, here's the listen. Now, they have a amplifier which is sensing the voltage here and then generating an error signal. Now, these two inductors are like a regular filter that normally you would put in order to reduce the ripple current. And in this case, however, they have this inductor which is coupled to these, and this error signal which is generated here is actually inducing a voltage on these two inductors opposing the noise which has been sensed, and thereby reducing the total current or ripple current that will go into the listen. So this is the idea behind this particular implementation. Aside from putting a transformer in series, there is a possibility of actually putting an active element, active device, like a transistor, a BJT transistor, or a MOSFET transistor. Now, the idea here is that we are sort of attenuating or eliminating some of the current by putting a element in series between the source and the load. This would be like the AC in the case of the input filter. This would be like the AC side, and this is the switch mode, the power supply, or the converter. So there are two possible implementations with BJT or a MOSFET. And actually the filter idea could take one of two possibilities, one which I call active operation and one passive. Let me start with this passive option. Again, this is the noise section. This is the output, which should be like the line, the AC line, or the listen, I should say. And this is the series element. Actually, this represents both a transistor BJT or a MOSFET because each of them can be modeled as a large resistor. And this is actually the slope here, and this is the output characteristic of either BJT or a MOSFET, and a current source. In the case of a BJT, it will be HFE times IB, and in the case of a MOSFET, GM times VGS. So in the passive situation or option, you control this current source to actually pass the DC. So the DC is passing through here because we have to pass DC, or low frequency I should say, between these two ports. And then we are left with this large resistor. Okay, this is slope. Both of these elements have large output resistance. And this resistance actually acts as a attenuator because of the voltage division here. Being a large resistor, it will attenuate the noise from here to here. Okay, so the passive means that this is just a resistor, a large resistor, which is attenuating the signal. Now, another possibility, which is more sophisticated, would be actually to modulate this current source. That is, not only that it passes the DC, but it also generates an AC which is opposing the polarity of this current. So we have a much larger effect on the attenuation. Actually, there are some commercial units that work along this line. I like to show, however, a circuit that has been published in a recent paper. This is a boost type power factor corrector with an active ripple filter. It looks complicated. Let me just go through it and see all the components here. So we start with this rectifier. It's a full bridge rectifier. Here's the capacitor. This is, however, a low value capacitance because we like to retain the half wave rectification. This is not supposed to be smoothed DC here, but rather to show the high frequency component actually coming from here. So this is a small capacitor. Then we have a boost converter. It's an inductor, transistor, and a diode, and an output section. Okay. Now we have a transistor. It's a BJT transistor in series. The current is flowing this way through this transistor. Now, this amplifier senses the voltage across the transistor and compares it to a reference. This is actually a comparator. As soon as this voltage is higher than this reference value, this comparator kicks and the transistor turns on. And by this, it will reduce back the voltage across this transistor. So whenever the voltage goes up, this turns on and it reduces it. So this actually controls the operation of the MOSFET, the switcher, so as to maintain a maximum value of a voltage across this transistor. Very important for lowering the power dissipation. However, there's another loop here, a feedback loop, and starting here with sensing the output voltage and comparing it to a reference. You like to keep the output voltage to a certain level. It generates an error signal. Now, you go and multiply this error signal, which is basically DC, maybe has some ripple, but it's a DC signal, with the waveform that you find actually here. So you sense this waveform, half wave rectification, and you multiply it to generate this half wave configuration or waveform, which is of course the value of it or the height of it dependent on the error signal. The larger the error signal, the larger will be this height. Now this waveform is compared to the actually current flowing here. And in fact, this feedback now forces this current to follow this waveform by generating an error signal going through an amplifier and feeding the base of the transistor. So this feedback now is responsible for making the current through this transistor, therefore the input current, having the waveform of a high wave rectification as needed for power factor correction. Because we like to have at the input, we like to have a sinusoidal current, and this will be accomplished if the current after rectification will look like this. So we force this current by comparing it to this reference, which has been generated, amplified, and fed to the base of this transistor. So this actually brings me to the end of this presentation. I hope you found it interesting and it'll be useful to you in the future. Thank you.